network works. Service-aware virtual network function migration based on deep reinforcement learning. I would like to divide into 6 sections to present this work. Firstly, introduction, the background of this work. First, with the explosive growth of fifth-generation networks, the growing demand for network service has driven the telecom industry to design innovative network architectures with network function virtualization and safely defined networking. Among to academic and industry, the combination of NFV and SDN is expected to revolutionize network operations, not only by dramatically reduce costs, but also by introducing new possibilities for enterprise, carriers, and service provider. With the extension of global internet service, network operator will further extend the communication coverage of this generation communication networks. Meanwhile, with the rapid development of new applications and services, it is indispensable to provide and deploy new devices continuously, which will result in the network resource and energy consumption of data center networks increasing rapidly. By aggregating satellite networks to boost current network, therefore, it is essential to derive innovative satellite terrestrial integrated network. In SDN, NFV enable SDIN network service can be implemented with service function chains, which consist of a series of chained virtual network functions by highly predefined sequence. These VFs are instantiated and executed substrate nodes. When the demand of VF exceeds the mapped substrate nodes and the linked resource concept, the network function will be validated, which will seriously affect the success rate of SFS deployment and service performance. In order to accommodate the temporary service demands, it is inevitable to orchestrate the VF migration among substrate nodes to improve service performance. However, most of the current works mainly focus on static threshold changing mechanism. In a real DC scenario, service requests arrive at the system randomly with the requirements and the network resource consisting of the underlying infrastructures dynamically vary over time. A static migration solution is unable to satisfy the dynamic property of the network and lead to function invalidation or service degradation. Despite the significant advancements in network thanks to the introduction of NFV and SDN technology, the migration tools still require additional research and development to reach an acceptable level of automation. To this end, the motivation of this paper can be unfolded in 3 aspects. Firstly, to avoid substrate nodes and link overhead, and guarantee service continuity with the randomly arrived service requests. Some AFF should be migrated from portals for the utilization of resource rationally. Secondly, existing migration mechanisms are prone to frequent migration. A reasonable mechanism should be designed to reduce the times of invalid migration and related network overhead. Finally, we should consider how to optimize the average performance matrix and long-time scale through VF migration for SFC with a certain life cycle and variable resource constraints. Given the above consideration, we investigate the VF migration problem by taking migration trigger mechanism and migration overhead into account. Especially, rather than focus on the detailed migration process, we primarily concentrate on the migration overhead of the network. Since the appropriate deployment of VF can increase the utilization of network resource, enhance the throughput of the system, and improve the adaptation to environment changes. Our intention is to optimize migration overhead for all affected FCS. For this purpose, the main contribution in this paper can summarize as follows. Firstly, according to the characteristics of VF migration and traffic dynamics, we pose a dynamic threshold trigger mechanism to avoid the frequent migration and system instability incurred by the existing migration trigger mechanism. Second, based on this mechanism, we model the migration overhead and power consumption and migration latence caused by migration jointly. Besides, a stochastic optimization problem based on Markov design process is formulated to describe the migration process of VFs. Furthermore, a service-aware VF migration scheme based on DRL is proposed. Finally, extensive simulation results are provided to demonstrate that the validity of our scheme and a survey of comparative experience with the existing works also presented. The next part is system model Considering a network setting which is constructed upon SDN-AF-enabled SDN network infrastructure, in which physical resources are provided to service through resource virtualization, as shown in figure. To simplify the analysis, we split the continual design time into types of T. When a service request arrives, the NFVI provides the appropriate NFVI load in terms of the resource requirement of the NFs. The network model described as follows. The substrate node topology is modeled on the undirected graphic GD equal to VD and LP, where VP and LP represent the set of substrate nodes and links respectively. The nodes are characterized by computing resource capacity CI max and memory capacity MI max. The link LIJ between nodes VI and VJ is characterized by the bandwidth capacity BIJ max. And the times 30, the resource occupancy can be devoted to U star T, and the resource capacity is represented as omega star T respectively, where star represents the type of resource. We structure the virtual network as an order set GV equal to VV and AV, where VV and AV represent the set of VF and virtual links respectively. There are two SFCs in virtual network are denoted as the set S, and the Q SFC contains NQ type of NFs, which is denoted to SQ. Each SFC is formed by diversified VF with a particular order and mapped to with an internal resource requirements. Each VF has a finity communicating resource requirement and assume it as a CQT and a casing resource requirement MQNT. The virtual link between adjacent VF in any CSQ are represented as L, N, and 1Q. Similarly, the finity bandwidth requirement of each virtual link L, N, and 1Q is denoted by BQ, N, and 1T. Generally, SFC SQ has a mechanism end-to-end lattice limiting, which can be set as DQ max. In order to describe the relationship of VFs, we define the binary variable XIQNT and the IJQ and E and M1T. The next part is dynamic threshold changing mechanism. When a resource occupancy reaches the threshold, the migration is triggered immediately, which can lead to frequent migration and reduce the stability of the system. To solve this problem, the paper firstly proposed a dynamic threshold trigger mechanism to evaluate whether to perform migration immediately and time selected by market chains. The resource demand interval for arbitrary VQN is assumed as 5QN min and 5QN max. This term first allocate resource with 5QN max to each function in the absence of historical information and parallel knowledge, and the system runs. The future resource demand can be estimated in the future through market chain after obtaining enough simple data of VQN. To model the resource estimation under each time slot T, we divide the resource demand interval 5QN max min and 5QN max into W section. And the capacity of resource in each section is lambda QN. Each section represents a different resource demand state. That is, the W section mapped to W state of VQN, and the resource capacity under each state is equal to the origin earning of the section. Thereby, the resource state lambda omega QN T can be considered as a uniform or continuous variation in time slot T. Then, the 1D market state transition marking of VQN is obtained by the statistical measure of PQN. On this base, the resource demand of VQN in the time slot T and 1 can be estimated from the CK equation by building a solid-state discrete marking chain model, which can be estimated as F omega QN. In order to smooth the migration process and determine the optimal time of migration, we assume that the resource capacity threshold as the eta max and denoted a migration factor epsilon to estimate the probability of overhead and exploration in the next time per T and 1. When epsilon greater than eta max, it indicates that the subject node or link are unable to meet the service requirement and the migration should be executed immediately. By this way, the migration is triggered only when epsilon of the created time slot is greater than a certain value and lasted for a period of time. In this section, we formulated an optimization model for the WNF migration problem. Due to the WNF migration consume certain energy and increase the network latence, we have considered that the power consumption and migration latence of WNF certainly based on the literature. Suppose that a linear model of power consumption where the traffic entered by the load. Hence, the power consumption of load Vi and the time slot can be expressed as follows: P, V, and T. We assume that all of the load are increased with the identical maximum data computing capacity zone, which represents the number of CPU circles that can be presented per second. Hence, the power consumption of SFC-SQ and time slot is given by PQT. The migration lattice of SFC-SQ is related to the location of the SFC virtual link mapped to the substrate link. Then the migration lattice of SFC-SQ and time slot T is the sum of the migration lattice of all links. So the migration lattice of SFC-SQ can be expressed as DQT. Consequently, the total migration overhead of SFC in time slot T can be normally visualized and expressed as follows: CT, where omega 1 and omega 2 are the corresponding weightings, and omega 1 and omega 2 equal to 1. Therefore, the WNF migration problem can be formulated as follows: where the constraints in 1 and 2 restrict the variable xi, qnt, and the ijqn and 1 to binary choice. The constraints 3 to avoid loads, overhead, and routing loss. The constraints 4 to 6 ensure the computing testing and bandwidth demand for the WNF deployed in each node cannot exceed the maximum resource capacity. The constraints 7 guarantee that an arbitrary virtual link must exceed a continuous path Aij between substrate node Vi and Vj to which the adjacent Vqn and Vqn and 1, and maintain the traffic that the inflow must be increased outflow. In order to make sure that the link delay between WNF nodes in any specific satisfy the end-to-end lattice increment, the constraint 8 is proposed. In this section, we introduce the theorem of MDP personally, then model the optimization problem to MDP and the detailed state action and reward of MDP in the paper are defined respectively. Furthermore, the other goals is introduced in detail. We model the WNF migration and the MDP to describe the migration process. Firstly, the transition process of WNF on NFV nodes for each time slot T, described as a countable SAPR. State S, each state S and time slot T and ST, where we denote the substrate network topology space and CMB state the computing testing and bandwidth demand state space over WNF respectively. Action A. H equal to Xt and Zt, where Xt and Zt, the X and Z represent the mapping action space of the WNF and the virtual link respectively. Translation probability P. After taking action AT in time slot T, state St will be transformed to the next state at T and 1 with the state translation possibility P. Reward R. In the time slot T, the DR agent can obtain a reward based on the current state and the selecting action. In the paper, our optimization goal is to minimize migration overhead, so we define the additive inverse of migration overhead as the utility reward for time slot T. The current cumulative discount reward and time slot T is defined as R pi T, and under the policy pi, the expected reward for a game action and the state can be referred as the Q pi STAT. Generally, Q pi STAT can be interactively expressed through the Berman equation. In order to obtain the optimal policy pi start, the RLR team need to select action in each state to maximize the Q pi STAT. The migration scheme based on DRL. According to the analysis, the optimal policy pi start is obtained from the optimal action of different state of equation. 12. Since the service required as well as data flow arrive in a real environment are random, the optimal policy can not be obtained by inserting the Berman equation for the action value function. In this paper, we propose a server-based WNF migration optimization scheme based on design to solve the problem. The detailed scheme for is detailed graph and figure. If the system set TSD and time slot T, the actor parameter network selects a deterministic action AT equal to pi ST and NT according to the policy pi, where phi is a parameter of the action parameter network, NT is the OU laws introduced to increase the implementation after taking 80 in the network, the engine return or feedback of the limitedly reward RT and the late state STN1 to the actor network, and actors the tuple SA are exposed to the ingredient replay pool B, which will be used in the train process, are stated in the following. According to critic network tracing and learning and actor network training and learning, the real-time WF migration algorithm beside TD3 and follow table. To evaluate the effectiveness and reliability of the proposed scheme in this paper, simulation validation of this proposed scheme and the performance compared with the proposed work are performed. We compare the FDQ scheme, our proposed scheme based on the dynamic through-head trigger mechanism code SA1F FM and the method based on TD3. So we can show experience setting due to the high computing complexity of the optimal problem. We consider a fully connected DCN scenario which contains 11 generator virtual nodes and a satellite node. The computing capacity and the memory capacity of all of subject nodes is uniform distributed in 11 to 300 MIPS and 120 and 300 MB respectively, and the bandwidth capacity of each NIC is generated rather in the 20 to 100 Mbps. In order to simulate the real environment, the resource demand of SFC is simulated by Ziyu. Bottom some process to according with the characteristic of paired order and perceived real data flow. To each of SFC consists of different type of WF conform to the uniform distribution of 3 to 6. The relevant simulated parameters are shown in table. To verify the coverage of the algorithm pursued by adjustment by the beta, we keep the alpha constraint as shown in figure 3. When beta, the loss function relative greater, which easily causes the gradient to hang around the mini value and make it difficult to obtain the optimal solution. As beta decreases, the detail becomes less accordingly, and the loss function coverage rate becomes slow, making the loss curve smooth. Therefore, beta is selected in this paper. The migration overhead versus different thresholds is shown figure 4. In order to analyze more especially the effect of the shortcut sake on migration overhead, the difference between competing memory and bandwidth resource request and the diversity in service performance between substrate nodes are terminally max. We fix 5 SFC in their work, and can be seen from figure 4. The migration overhead gradually decreasing and the eta max screen increase. This is because the larger the eta max, the less likely the resource demand or will extend eta max, and therefore the fewer migration need to be performed, increase this overhead. It is necessary to discuss the migration overhead for our first scheme, as shown in figure 5a. We can observe that the migration overhead increase constantly and the number of SFC increase. Under the same service request, the total migration overhead of SA1FM is always lower than the of FDQ. Well, it can be seen that the overhead of SA1FM lower than DDS base. That is, the former can be further reduced overhead by adapting or migration mechanism compared with the later. Figure 5b shows that times of migration is figured by under the different algorithm. Compared with DDS base and FDQ, we notice that SA1FM can reduce the times of migration respectively, which is because the SA1FM can recently determine migration time to reduce migration times and improve the stability of the system. Finally, we can conclusion. In this paper, we studied the WF migration optimization problem in SDN and label SDN. WF are deployed in DCN. In order to avoid frequent migration, we firstly propose a dynamic through-head trigger mechanism and then formulate the problem and the stochastic optimization model with an MDP MNT meaning the migration overhead. To solve this problem efficiently, we resort to DRL-based service area where migration scheme to obtain the feasible solution. The simulation resulting shows that the proposed scheme can effectively avoid frequent migration and reduce the migration overhead.